Your laptop is built from tiny switches, flipping between 0 and 1. That simple choice is the language of every classical computer. But quantum computing asks a stranger question. What if information could live between answers? A classical bit is definite. It is either 0 or it is 1. Think of it like a light switch, off or on. 8 bits make a byte, enough to store a letter, a number, or an instruction. Classical computers are powerful because these choices are stable and easy to read. But they still process information as definite states, step by step. To go beyond that, we need a different kind of unit. That unit is called a qubit, a quantum bit. A qubit is not just a tiny switch. It is a controllable quantum state. A useful way to picture it is a direction on a sphere. The top of the sphere can mean 0, the bottom can mean 1, but the arrow can point anywhere on the surface, not just at the poles. That direction carries amplitude and phase, the hidden numbers that guide later results. So the important object is not a single answer. It is a state we can gently rotate, mix, and measure. This is where superposition enters the story. Before measurement, the qubit can behave like a blend of 0 and 1. A spinning coin is a good metaphor. Not heads, not tails, until it lands. The amplitudes pull the final result toward one outcome or the other. Algorithms work by shaping those amplitudes before anyone looks. Useful answers can reinforce each other. Wrong paths can fade away.
Measurement is the moment the rich state becomes a normal result. The detector looks at the qubit and the possibilities collapse. In one run, you see only 0 or 1, never both. But if you repeat the experiment many times, a probability pattern appears. A quantum program prepares the state, rotates it, and measures at the right time. The goal is to make the useful answer more likely than the useless ones. So timing and control matter as much as the qubits themselves.
Superposition is only half the story. The other half is entanglement. When two qubits are entangled, they share one connected quantum state. That does not mean they are sending messages faster than light. It means their outcomes are correlated in a way classical bits cannot copy. Measure one qubit, and the shared pattern shows up in the other. Einstein called this spooky action at a distance. He disliked the idea, but experiments showed nature really allows it. Quantum algorithms use this shared structure to make qubits work together. Classical computers use gates like AND, OR, and NOT. Quantum computers also use gates, but they change states by rotation. The Hadamard gate creates a balanced superposition. The X gate flips a qubit, while phase gates change its hidden angle. The CNOT gate links two qubits, creating entanglement inside a circuit. A quantum circuit is a recipe. Prepare, rotate, link, and then measure. Having gates is not enough. You need clever algorithms to use them. The trick is interference. Waves can add together or cancel out. A good algorithm makes the right answers louder. It also makes many wrong answers fade into the background. Shor's algorithm threatens RSA because it can factor huge numbers differently. Grover's algorithm searches large spaces with fewer steps than a classical search. Quantum computers are not faster at everything, only at the right kinds of problems. But here is the catch. Qubits are incredibly fragile.
Heat, vibration, or even stray light can disturb the state. That disturbance is called decoherence, and it can erase the computation. Engineers fight it with shielding, calibration, and extreme cooling. Error correction spreads one logical qubit across many physical qubits. Protecting the state is one of the hardest parts of the field.
Real quantum computers look less like magic and more like strange laboratories. Superconducting qubits are tiny circuits cooled near absolute zero. Trapped ions use single atoms held in place and controlled with lasers. Photonic machines use particles of light, sometimes at room temperature. Each approach trades speed, accuracy, cost, and scale in a different way. That is why hardware is still an engineering race. So where could quantum computers help first?
Chemistry is a natural target because molecules are already quantum systems. Optimization and sampling could help with logistics, AI, and complex planning. Cryptography may also change, pushing the world toward quantum-safe security. It is not magic, but for some problems, the payoff could be huge. So here is the clean mental model.
Qubits hold amplitudes, not just ordinary 0 or 1 values. Gates reshape those amplitudes step by step. Entanglement lets several qubits share one connected state. Measurement turns the final pattern into a normal answer. The race is to keep fragile states alive long enough to be useful. That is quantum computing. Thanks for watching.